ሰላም እንዴት ናችሁ? ዛሬ ከሊኒያር ሪግሬሽን ተነስተን እስከ ላርጅ ላንጉዌጅ ሞዴልስ ድረስ ኩዊክ ጆርኒ እናደርጋለን። A journey from explainable models to powerful mysterious word salad generators. And basically we will do a drive through በጣም በስፒድ ነው የምንሄደው and we will talk about a little bit compressed detail of concepts in between. መጨረሻ ላይም I have a joke for you, an interesting joke, so forward አድርጋችሁ እንዳታዩ, just keep going with me. Yeah, so let's do it. Overview ስናየው linear and logistic regression, which we all know, basic የሆነው idea, basic notationዎችን እናያለን. And then we also talk about neural network, the fundamentals of neural network, what it is and how it works. And also እዚህ ጋር ከኒውራል ኔትወርክ ጋር አያይዘን multi-layer perceptron አብረን እናነሳለን. And then we will talk about back propagation and how it works, and neural network for sequential data or time series data, or also language is also temporal, consider that temporal element. So we'll talk about it. And the most interesting part of our current knowledge, attention mechanism, how it works, and then እሱን ተከትሎ ደግሞ ትራንስፎርመርስ እንዴት ነው የሚሰራው፣ all the large language ሞዴሎች የሚጠቀሙት አርኪቴክቸር ነው። ስለ ትራንስፎርመር እናወራለን and the hilarious joke at last. Okay. Yeah, obviously linear regression አብዛኞቻችን ሰርተንበታል እናውቀዋለን. So one of the simplest and foundational machine learning model is a statistical learning model. So it assumes a linear relationship between x and y, and y, or the weights transpose times x plus b. This is the linear function, and this guy. And the objective is to minimize the mean squared error. That means you can see that so the best fitting line መፈለግ ነው the core idea of linear regression. So this the loss is minimizing the loss or the squared error, the y minus the predicted y, and then divided by the sample size. So used for prediction, feature importance, and trend modeling. So this is clear that we can use linear regression for multiple tasks. ከዛ ግን it was not enough by itself. And then ምክንያቱም እዚህ ጋር we have only linear relationship, and if something ከራሱ ከዚህ fitting line ተነስታን ብናይ overestimate ይደረጋል some point, and we leave unaddressed የሆኑ data points. ስለዚህ we need more complex modeling than linear regression. We got logistic regression. Logistic regression ምንድን ነው? It's basically used for binary classification problem, and it applies the sigmoid function to the model probabilities. And so the application of sigmoid function to the linear model. You already saw this guy, right? ይሄ ማለት ነው. So applying this sigmoid function to the linear model, and then you get sigmoid function. So ምን ማለት ነው? You have a value, and the value will be adjusted to between 0 and 1, and then that means you have two class problem solved ማለት ነው። ወይም የክላስ yes and no, or 1 and 2 class problem ቢኖራችሁ you can solve such kind of problem. And the loss is the cross entropy loss. This is the loss. It's minus log of y plus this is the predicted the predicted value of y and this yeah, so 1 minus y and y here, so the rest, the one component and the 1 minus y component, the rest of it ማለት ነው because this is since it is bimodal ስለሆነ or two group ስለሆነ ያለው yeah, 1 minus y and y here, you have the log of y and the log of 1 minus y. So this is the formula for cross entropy loss. Then you have a problem solved. So in the logistic regression model, you can yeah, you can model a problem that has classification of two groups, right? So this is still linear, but outputs probability in 0 and 1. So this still assume there is in the background there is a linear relationship. Also, you can see it here a little bit linearity. Then ከዚህ ስንወጣ ለምሳሌ የኤክስ we'll talk about it. Why go beyond linear model? So linear models can only capture linear relationship, right? This is obvious, and many real-world patterns are non-linear. This is also clear that the world is not linear, as simple as that. The XNOR or the XNOR or the XOR logic gate, the XOR problem የሚባለው ለምሳሌ if you have so if you have this problem, if you have 0 0 1 0 or 0 1 and 1 1 data points, that means the X is, this is a logic XOR logic, and እዚህ ጋር you cannot fit a line here. ለምሳሌ በዚህ straight line or linearly እነዚህን ፖይንቶች ክላስተር ማድረግ አትችሉም። ሆሪዞንታሊ እንደዚህ ብታደርጉ you cannot appropriately ሁለቱን አረንጓዴዎች አንድ ላይ ክላስተር ማድረግ አትችሉም or ሁለቱን ቀዮች አንድ ላይ ማድረግ አትችሉም። So a linear model cannot solve this problem ማለት ነው። ከዛስ what's next? We need more complicated model ማለት ነው። So linear regression fail on these tasks. ለምሳሌ vision task ላይ curves, texture, language, context dependent meaning. ስለዚህ all the complexion of non-linearity create problem for linear models. So we need a model that can learn non-linear decision boundaries. That means a decision boundary that እችኛዋን የግሪኑ ያለበትን ብቻ ከፍሎ yeah, this is A and maybe ይሄን ለብቻው የሚያወጣ or እዚህ ጋር እና እዚህ ጋር አድርጎ የሚከፍል some kind of non-linear or polynomial boundary ያስፈልገናል ማለት ነው። So the solution now become neuron plus activations. We'll talk about what's activation and what neuron is. It's very simple. And then we'll talk about multi-layer perceptron. በመጀመሪያ ግን ኒውሮን ምንድን ነው? ኒውሮን ማለት ኒውራል ኔትወርክ የሚለው ኮንሰፕት ፋንዳሜንታሊ ከሂውማን ብሬን ቲንኪንግ ጋር ነው ተያይዞ ነው የመጣው። so the neuron is this የሚያስበው or rational decision or the smallest element in the decision making process ማለት ነው። So in the neural network or in the machine learning context, a neuron is a fundamental unit of a neural network, the basic unit, and it receives input, applies weight, add bias, and uses an activation function. And it mimics behavior of biological neuron, as I said. So in a simple and clear way, በዚህ ምስል ላይ እንደምታዩት ለምሳሌ you have input x1 x2 to xn ቢኖረ this could be image, this could be tabular data, this could be anything that you want to analyze or process, and you have a bias term. Then we assign weights to each inputs, so the weight is assigned randomly at the initial, and then it's learned through time through ወደፊት እናየዋለን back propagation ላይ. So we have weights. The weights are summed. This is this weighted sum. and then we apply some activation function to the weighted sum and we have output ስለዚህ ይህ output ደግሞ depend የሚሆነው based on the activation function ነው ለምሳሌ ሲግሞይድ አክቲቬሽን ፋንክሽን ሲኖረን አውትፑታችን ቅድም ሲግሞይድ ወይንም ሎጂስቲክ ሪግሬሽን እንዳየነው ሲግሞይድ ፋንክሽን ሲሆን see so it lies between 0 and 1 so if the activation function here is sigmoid then we have an output of between 0 and 1 and hyperboloid tangent ሲሆን rectified linear unit ሲሆን leaky ReLU ሲሆን max out ሲሆን we'll see what the activation and what it does so basically this is what a simple neuron looks like so what happens inside the neuron is መጀመሪያ you have the weights you have a weighted sum and then you apply activation to the weighted sum and then you have output yeah so the basic አሁን አብዛኛውን ጊዜ የምንጠቀማቸው activation functions tangent hyperbolicus tan h ReLU sigmoid and leaky ReLU ናቸው tangent hyperbolicus ማለት the output will range between -1 and 1 that means anything that your model output የሚያደርገውን it will shrink or I don't know convert it into some value between -1 and 1 ReLU is rectified linear unit so that is እንደምታዩት እዚህ ምስሉ ላይ anything that is below 0 will be 0 and anything below after anything above 0 will be considered as will be passed or will be outputted after the activation so ምን ማለት ነው everything unimportant is equally unimportant I think in somewhere ያዩት መሰለኝ so the point is rectified or ReLU ምን እንደሚያደርገው it takes the maximum of the positive value or it will ignore the negatives and the sigmoid we've talked about it and it's range between 0 and 1 yeah and leaky ReLU is also a version of ReLU but it allows some values some small leaky of values from the negatives so this so ይህንን apply እያደረጋችሁ you can have some reason argument about which activation function to use and you can decide based on your purpose so activation function ማለት ይሄ ነው ስለዚህ ይሄ ማለት ምን ማለት ነው so እዚህ ላይ የምታዩት እቺ የactivation function this is for sigmoid specifically but this is activation function ማለት ነው activation function will be applied in the weighted sum ማለት ነው this weight times the input and this weight times this input this weight times this input and the same and then you have the sum so that's how weighted sum ማለት ያ ነው and you apply sigmoid to that and you get an output yeah activation አይተናል so from here we can see that this is a neuron so neuron ብቻውን ምንም ሊያደርግ አይችልም ከዛ ምን ይመጣል we will stack these neurons together and we create layer of neurons ያንን ምን እንለዋለን multi-layer perceptron ይባላል ማለት ነው A multi-layer perceptron is a type of feed-forward neural network and consists of input layer, hidden and output layer. So input layer የሚባለው the layer, obviously the input layer, and the hidden layer could be as many as needed for your architecture. And the output layer is the output layer, of course. And each layer is fully connected to the next. So this is also sometimes called feed-forward network ያ ማለት ምንድነው each neuron is connected to another one and so in this connection important የሆነውን feature of the data will be learned through the process ማለት ነው ስለዚህ ከዚህ ወደዚህ ሲሄድ ኢንፎርሜሽኖች ናቸው የሚያልፉት you know after applied activation so there will be weights passing through, and important features will be learned at the end. So basically this is what multi-layer perceptron is, and for feed-forward network also used interchangeably with MLP, as I said, and information flow is on one direction, no cycles. So this is directed acyclic graph, or this is only one way feed forward, and common in both classification and regression tasks. So it's clear. So at the end, you have a classification or regression problem solved. But the problem is feed forward network doesn't know how to adjust its weight. So the network can't reduce its error over time, and as layer increase, it becomes harder to trace how outputs depend on inputs. So it lacks a way to know whether it is getting better or worse. So I think እዚህ ጋር clear ነው. So it's only one directional ብለናል. So certain weights, certain activation, it goes to this one, and then certain weights, ይሄ ሁሉ ከዚህ ይቀበላል weights. You got some weights here, then ይሄ pass ያደርጋል፣ ወደዚህ pass ያደርጋል፣ ወደዚህ pass ያደርጋል. So this it learns feature, and at the end you have an output, right? But is the learned output is correct የሚለውን ነገር you cannot know, right? ስለዚህ in a nice way they come up with a solution to achieve that, to achieve the problem with it lacks a way to know whether it is getting better or worse የሚለውን they solved it by using back propagation. So back propagation idea ምንድን ነው? is to minimize the loss. So loss ማለት already ቀደም define አድርገናል. It's the difference between the predicted and the true value of y, and that's to minimize y we want smaller loss, and by updating weights using the gradient descent. We'll talk about gradient descent I think in the next slide. And yeah, so the idea is to update weights using the gradient descent methods. There's also other methods, but mostly gradient descent. And we apply chain rule across layers with the back propagation ጊዜ ማለት ነው. So how is it applied is the partial derivative of the loss function with respect to the weight ማለት so the loss with activation A, and the chain rule ማለት I hope you know chain rule, right? So the partial derivative of the loss function divided by the partial with respect to partial derivative of A times partial derivative of A with respect to Z, and partial of Z with respect to W. That means the activation, the output of the neuron, this Z is the pre-activation, and the weights, everything እዚህ ጋር ከዚህ now you get the output አይደለ? The outputን ካገኛችሁ በኋላ you have a loss here, so some value of loss, and that loss will be used to calculate the how much of each neuron or each weight is responsible for this loss. ግልጽ ነው? so የትኛው weight ነው ለዚህ ሎሱ እንደዚህ this amount እንዲሆን የትኛው ሎስ ነው more contributing የሚለውን ነው more calculate የምናደርገው. so with respect to each layer እንደገና ወደ ኋላ እንመለሳለን ማለት ነው, right? so by doing that so እሱን የምናደርገው with gradient descent ነው. gradient descent ምን እንደሆነ እናወራለን, ግን the idea of back propagation ግን ወደፊት ሄደን ሪዘልት እንዳገኘነው ሁሉ ለርን አድርገን ሪዘልት እንዳገኘነው ሁሉ and then we try to minimize the loss with back propagation, and trying to find the least the least loss that we can achieve from learning. I think that's yeah, a little bit complicated concept, no? Again, easily it looks like that. So gradient descent. Gradient is an increase, an abrupt increase of some elevation or gradient ማለት, and gradient descent is the opposite, the negative direction of gradient ascent, of course, and gradient of a loss flows backward layer by layer. ቀደም እንዳልኩት layer by layer ነው gradient የሚሄደው. Yeah, so the error at layer L, or this is the gradient, or where the error at layer L is calculated by the weight at the next layer times the times the error at the next layer as a function of yeah. So weight update rule, weight update የሚያደርገው ምንድን ነው? weight is updated by the weight that you have now minus the learning rate. Yeah, this is the learning rate here times the chain rule, or the partial derivative of the loss function with respect to each weight. So learning rate ማለት ምን ማለት ነው? This is a very clear example or nice example of gradient descent. ለምሳሌ in the top of the mountain ቢሆን አንድ ሰው ከዛ አይኑ ቢታሰርና if he cannot see anything, ኦብጀክቲቭ ወደ ታች መውረድ ቢሆን ኦብጀክቲቭ፣ so የመጀመሪያው ነገር ምንድነው የሚያደርገው? he take a random walk to one direction and see if that takes him a little bit down አይደለ? ከዛ እዛ ጋር ሆኖ he just take one step. so learning rate ማለት ያ ነው, a step at a time you take to find the local minimum, ultimately looking for the global minimum. So using this approach you will find the global minimum ideally. That means the ሎሱ ዝቅተኛ የሚሆንበትን አገኘ ማለት ነው. So that means your learning is very nice. This is the concept of gradient descent. So the idea of back propagation and gradient descent and feed forward networks works very well, but the problem is why this is not enough is when it comes to sequential data. Sequential data ማለት ነው ለምሳሌ የዲኤንኤ ዴታ ሊሆን ይችላል፣ የጂን ዴታ or longitudinal data, time seriously collect የሚደረግ blood pressure every day for months, cohort or something. እንደዛ አይነት ዳታ ሲሆን እነዚህ ሜቶዶች or feed forward network doesn't work because it considers an input without the time dimension or the recurrence of something. So they lack memory. Yeah, ማለት we have to have some sort of memory to model such kind of sequential events, right? So no awareness of the order or context in a sequence. So they cannot handle time series data, they cannot handle text sequence, audio, video. Yeah, so example, he went to the, yeah, so if a feed forward network cannot infer, store or park without knowing prior words because it does not have the capacity to remember or utilize previous inputs. Yeah, so it's only predict based on what it sees, right? So yeah, so it processes each input independently, so it lacks the contextual understanding that might be necessary to make such inferences. So no temporal memory. What comes next? A temporal problem solve ለማድረግ there is an idea of adding some component to this feed forward network and come up with the idea of recurrent neural network or RNN. So RNN are designed to handle sequential data by introducing memory or the idea of short-term memory and maintain a hidden state or HT that captures information from previous time step. And the core idea ምንድነው? The current state or the hidden state of the current hidden state is a function of the weight of the weight times the input of the current input. Yeah, the input times the weight and plus the U matrix of the previous hidden state plus B. So the only difference is this component here, where xt is input at time t, hidden state from previous activation function. So the output depends on both current input and past context. So idea ምንድነው? It enables understanding of language or time series and structured sequence. So እዚህ ምስል ላይ እንደምትመለከቱት this is an ordinary feed forward network. ያ ማለት you have input x, you have the weight matrix already አይተነዋል ቅድም። input x and weight matrix ማለት simply እዚህ ጋር ያየነው ማለት ነው። this is the input weight and this is the weight, the input and the weight matrix. And you sum it up. This is a weighted sum, and then you have the hidden state and the hidden layers, and then you have the matrix here, and you have the output, or you softmax over the output, and you get some probabilities. So the idea of recurrent neural network is to complement this feed forward network with መሀል ላይ እችኛዋን the output from previous hidden state sum ማድረግ ማለት ነው። ስለዚህ ht was ideally ምን ነበር? wtx ነበር። ያ ማለት weight times tx ነው htx የሚሰጠው right? ht የሚሰጠው. So in this case this hidden layer or hidden layer from the previous node will be taken as an input to sum up. That means ሞዴሉ ምን ያደርጋል? It will be aware of its near context ማለት ነው። So this problem is solved. This is a very nice and interesting progress in dealing with sequential data. But this idea is also with limitations. So standard recurrent neural networks struggle with long-term dependencies. So እዚህ ጋር እንደምታዩት እቺ hidden state, this encode everything that happened before, right? So this is a very kind of short-term memory. So struggle with long-term dependencies. ለምሳሌ the cat with the dog chased በላንጉዌጅ ሞዴል ስንመጣ ረዘም ያለ ቃል ሲኖር the cat የሚለውን አይዲያ the cat which the dog chased was dash ብንለው by the end of the sentence the model will forget that we were talking about the cat, right? So the other problem with recurrent neural network is the vanishing and exploding gradient. So እዚህ ጋር ቅድም ያላነሳሁት ነገር with recurrent neural network, this is only for one input for xt, right? But this keeps on unrolling ይባላል. So this will happen for every input. ያ ማለት this will be ይሄኛውን ኢንፑት ለሚቀጥለው አንሮል ያደርጋል፣ ይሄኛው ደግሞ ለሚቀጥለው አንሮል ያደርጋል። So by the end ምንድነው it's a huge or based on the number of sequence that we are trying to handle. ለምሳሌ የስቶክ ማርኬት ከሆነ እያየን ያለ ነው። የ10 ቀን ስቶክ ማርኬት ከሆነ 10 ጊዜ አንሮል እናደርጋለን and if we do 50 that means yeah, so it's the formula to the power of n ነው. So to the power of 50 or to the power of 10. So the more sequence lengths we have, the more unrolling we do, and that creates vanishing and exploding gradient. ያ ማለት during backpropagation ቅድም backpropagation ላይ we are calculating the derivative of each layer backward አይደለ? So if the derivative, the result from the activations are bigger in larger in some layer, ወደ ኋላ እየሄድን በመጣን ቁጥር right, it will be it will get bigger and bigger. And also the same if we have smaller number, ትንሽ ከሆነ ቁጥሩ we have multiplication of small numbers again and again. That creates very small gradient. ያ ማለት ዜሮ ግራዲያንት ሆነ ማለት there is no learning at all ማለት ነው. And explode also, this is very big, there is no learning in that sense. Yeah, so back propagation ላይ through time ስናደርግ if we have large time sequence in each layer ስለሆነ የምናደርገው it will be hard to compute this, and we'll end up having no learning. So it's difficult to train to retain useful information from long sequence basically. So learning long range pattern example እንደጠቀስኩት is unreliable, and training become unstable and inefficient for large context because of the exploding gradient. Yeah, so the cat which the dog chased was dash. We want the model to predict that chased was mine or something like. ስለዚህ recurrent neural network it will predict some word, but the context window for it to predict will be won't comprehend that, won't or will not consider the context cut at this time. So it will forget ያደርጋል ማለት ነው። only short term ነው or the close distance ያሉትን ወርዶች ነው የሚመለከተው ማለት ነው። So we need a better solution, or we need a better memory mechanism. Then comes long short term memory algorithm. This is an interesting one because this long term dependency problem is solved with this algorithm. ያ ማለት ምንድን ነው? It introduced a special memory or cell to store long term information, like እችኛዋ, this one, the context cell እንላታለን. And it also uses gates to control the flow of information. So basically long short term memory or LSTM ማለት it's a recurrent neural network, but a gated recurrent neural network. What are the gates? The first one is the for gate, the input and the output gates. ምንድን ነው የሚያደርገው? So you have a for gate, decide what to discard, and also in other sense what to remember as well. So the for gate is this one. This is the F, the for gate. ያ ማለት ምንድን ነው? You have the hidden layer information, and you have the input, and you weight sum that and apply sigmoid, and then you get the for gate. So ያ ማለት ምን ማለት ነው? sigmoid እዚህ ጋር apply የሚደረገው sigmoid function because we have 0 and 1, right? ያ ማለት we only have values from 0 to 1, and the dot product here is applied to the context, or the context from the previous node. So that means this will be carried out in long term. So it will be ይሄንን multiply ያደርገዋል, ግን since this mostly this will be closer to 1 or 0.9 something, or something in between based on the result. Again, anyways, we don't have negative value, or we don't have 0 for that matter, because እዚህ ጋር 0 ሆነ ማለት we do multiplication or dot product with this one, that means the context or this memory cell will be 0, so this will be disqualified. So in any way we decide what to carry on in the process. And the input gate also, this is the input gate. You have this weight matrix, and you apply a sigmoid function, and then you this is the recurrent neural network gate, which applied tangent hyperbolic activation, and then እዚህ ጋር dot product ይደረጋል. So the context goes through the process. ያ ማለት by the end of the computation of the next word, the model will still have an information about what was happening before. That's in a nutshell. So there's a lot of computation. Maybe in the next practical Python code details, and we can see how to define those things. So the idea ምንድነው? It help avoid vanishing gradient and capture the long-term dependency. So it's more effective than vanilla neural networks, recurrent neural networks. So vanilla ማለት just so it's vanilla. And language modeling, speech and time series mechanisms, machine learning, and so language translation and so on. So the basic difference ምናየው feed forward network ላይ you have an input x, you weight it, we have a weighted sum, and activation you got h, or the hidden state, so to say. And for the simple recurrent neural network, you have the input at t. So here the time component አለው እዚህ ጋር input xt, and you have the hidden state from the previous time t, and you have the weighted sum of that one, and you get activation. Boom, you got the hidden state at time t. And when it comes to long short term memory, input ላይ የሚገባው ምንድነው? the previous context or the memory cell here እዚህ ጋር እንደምታዩት, and then the hidden layer from time t minus 1, the previous one, ልክ እንደ RNN እንዳለው ማለት ነው. And then you have the input, and at the output you have the current state, and the current hidden state, hidden layer, and the context. So this will be ይሄ እንደ input ለሚቀጥለው unrolling ያገለግላል ማለት ነው. For every sequence, then it goes on unrolling, and at the end you get more comprehensive and more context sensitive model of that works for sequence data or language stuff. But this is also with limitations, and even with long short-term memories, sequential model face key bottlenecks. So እዚህ ጋር maybe ስለ encoder decoder እናወራለን፣ ግን እዚህ ላይ ያለ አይመስለኝም. Anyways, let's go on. The problem with LSTM is no parallelization. That means it's a sequential activity, must process input step by step. That means it's slower for longer sequence, and it's very computationally intensive. Limited context window ማለት okay, attention ላይ እናየዋለን እሱን. It's hard to capture dependencies for far apart in text. This is from recurrent neural network limitation. Memory bottleneck and back propagation through time is still complex and unstable. So we need a model that handles sequence in parallel. Cool. And focus on relevant information regardless of position. So the cat የሚለው ነገር ከሴንቴንሱ መጀመሪያ መጣ፣ ከሴንቴንሱ ሚድል መጣ፣ የትም መጣ፣ it will የምንፈልገው ሞዴል መጨረሻ ላይ ፕሪዲክት ስናደርግ ስለ ካቷ እያወራ እንደሆነ ማወቅ አለበት ነው። ሶ ኮንቴክስቱን የተረዳ ማለት ነው። right? And what comes next is the foundation of everything. ስለ ላርጅ ላንጉዌጅ ሞዴል በሙሉ ይሄ ኦፕን ኤአይ ምናምን ሁሉን ፋውንዴሽናል የሆነው አይዲያ የመጣው the transformers and attention mechanism ነው። Okay, attention mechanism. What's attention? Attention lets the model focus on relevant part of the input sequence. So attention mechanism, attention, the word is clear. I think the publication from 2017 title rasu attention is all you need. So I recommend to read the paper. It's very nice and very detailed. So attention ማለት lets the model focus on relevant part of the input sequence. It computes a weighted sum of all sequence positions, which is great. And basic idea ምንድን ነው? You have ለምሳሌ የሆነ text ቢኖር the text will be grouped into query. You have key and value. The attention does is ለሶስት እንደዚህ ይከፍለዋል. Then attention will be calculated by the softmax of query times the key transpose divided by the dimension of the key. So this sounds a little bit complicated. Can possibly, yeah, I have it here. So idea ምንድን ነው? ለምሳሌ the chicken didn't cross the road because it was too tired, right? So it የሚለው ቃል እዚህ ጋር the query, let's say this is the query. it የሚለው ቃል ምንን ነው ሪፈር የሚያደርገው ብለን ስንጠይቅ the chicken didn't cross the road because it was too tired, right? This refers to the chicken definitely አይደለ? እንደ ሰው ስናነበው ዶሯ ደክሟት ነበር። But what if this sentence, a query, the chicken didn't cross the road because it was too wide ቢሆን ኖሮ wide like ሰፊ. So this it probably attends more to the road. So እዚህ ጋር ከለሩ የሚያሳየው this is a little bit more highlighted, right? ደመቅ ያለ ነው። እዚህ ጋር ደግሞ ለስለስ ያለ ነው። So this is more likely ብሎ ነው በዚህ ጋር suggest ያደረገው. And if this was wider ቢሆን ኖሮ probably this will attend more to the road layer. So a lot of computation goes in this. These are the keys and the values. I think more detail አንድ ቻፕተር አንድ ቪዲዮ እንሰራበታለን። አንድ ቻፕተር ሰጥተን እናወራበታለን። what the query ማለት ምንድን ነው? key and value, how do we do the matrix multiplication and everything. We'll talk about it again. For now, as a highlight and as a drive-through, this will be enough. Yeah, so the query is what we want to find. What we want to compare against is the key and the information we aggregate. So the idea is it will enable the parallel process and better long-range dependency. Yeah, so this is the very nice representation of how self-attention works. So self-attention is a special case of attention, and you have query, key, and value come from the same input sequence. You have an input sequence. ለምሳሌ የቅድሙ the chicken ምናምን የሚለው like you can take it as a sequence, and the same sequence will be used as query, key, and value, and allow each token to interact with each other, every other token. So token ማለት every word ማለት ነው in this case, and we allow each token to interact with each other and learn relationship or dependencies and meaning between words. So regardless of the position ማለት ነው። ቅድም ያነሳናቸውን ፕሮብሌሞች ሶልቭ ያደርጋል። So for each word, compare it to all other words, compute weights, how much to attend to each one. So it aggregates information using those weights. So እችን image ስንት አይነት ናት? You have the embedding. So input 1, input 2, x3. This has the sentence and 1 by d dimension. So for every input, we have the weights of the key, the query, and the value. Key, the query, and the value. We generate these vectors, right? And the second stage is to compare query with keys. Query with key ማለት the dot product of the query and key. We have key here and the dot product of the query and key. ኩዌሪ ማለት የምንፈልገው ነገር ነው። ኪ ማለት is what we compare against to ነው። so basically we do a dot product. Dot product ማለት is also a measure of similarity in many cases. So we do a dot product between the key and the query, and the key and the query እዚህ ጋር እንደምታዩት this is operation is dot product and the key and the query. So you got the dot product. And the third level ምንድነው? We divide scalar score by the square root of the dimension of the key, the length of the k ማለት ነው. So this is a normalization task, and then turn into alpha ij weights via softmax. So afterwards we apply softmax and we multiply each with the value that so እዚህ ጋር የምታዩት weight each value vector. So we have the value vector, we have the computed stuff from here, and we multiply everything like እንደዚህ ከዚህ እንደመጣ ሁሉ እዚህ ጋር ዶት ፕሮዳክት አለ በዳይሜንሽን እናካፍላለን we softmax over the stuff and we directly multiply it with the value vector እዚህ ጋር እንደምታዩት and then we sum together, then we have our, so to say, the attention or attended wording. So በዚህ way we can solve a problem. ስለዚህ እዚህ ጋር ይሄንን አይነት ፕሮብለም ሶልቭ ማድረግ እንችላለን። so the chicken eats ሲሆን I mean that is tired. Based on this context, this is referring to the chicken. If it's changed, it could be road. So different attention will be given to different context, different things based on the context you have. So that's the idea of attention. But and attention ብቻ, this is called attention head. And attention head ብቻ በራሱ it won't be enough. We need to stack them up together, and instead of computing a single attention, we compute multiple in parallel. ስለዚህ ምን ማለት ነው? each head እዚህ ጋር ይሄኛው ለአንድ head ነው. you stack this multi head attentions. Oh, so this is the linear, so this must be the heads then. Yeah, so this will be the heads, multiple heads, and ያ ማለት ምንድነው? አንድ ወርድ በተለያየ ኮንቴክስት ውስጥ ምን አይነት ሚኒንግ አለው የሚለውም ጭምር እንማርበት ለርን ያደርጋል ማለት ነው ሞዴሉ። and parallel computation is achieved, and we have much better model to understand sequential data. So basically each head learns different pattern, examples syntax, position, semantics, learn ያደርጋል, improves model capacity and generalization. It enables the transformer to jointly attend to information at different position and representation. So basically እኛ ሰዎች በምንረዳው አካሄድ የአንድን ወርድ ኮንቴክስቹዋል ሚኒንግ ኮንቴክስቱ ሲቀየር ፖዚሽኑ ሲቀየር ቤዝድ ኦን the context ለርን ማድረግ ይችላል ማለት ነው። yeah, some heads learn the syntax, some heads learn the syntactic and semantics and whatsoever. So in multi-head attention leads to the big idea of transformer architecture or transformer. So now multi-head attention ተመልከቱ። አሁን እዚህ ጋር የደረስነው ከሊኒየር ሪግሬሽን ጀምረን ነው ራይት። ሊኒየር ሪግሬሽን ስንል ሊኒየር ሪግሬሽን ደግሞ ወደ ውስጥ ሲገባ ምንድነው ራፕ ሲደረግ ሲጠቀለል በሎጂስቲክ ሪግሬሽን and ሎጂስቲክ ሲጠቀለል ኒውራል ኔትወርክ ሲጠቀለል ሰው ፎልዲንጉ አሁን ትራንስፎርመር ላይ ደርሰናል። ትራንስፎርመር ማለት ምን ማለት ነው? ትራንስፎርመር block is composed of 4 key building blocks, and the first key building block is the multi-head self-attention, which is this one, already ያየነው ነው, and this is composed of different attention heads. ስለዚህ የመጀመሪያው multi-head attention ነው። ከዛ add and layer normalize, so layer normalization layer አለ, and then we have feed forward network, and we have another normalization. So in the transformer architecture we have 2 normalization layers and 1 feed forward network, and one multi-head attention layer. Each token learns by interacting with all other in parallel, and residual connection improve gradient flow. So stacked indexes like ከ6 stack of transformers can be stacked. Transformer block can be stacked. ለምሳሌ OpenAI was 96 layers, maybe, I don't know, I think ይመስለኛል. Forms the backbone of most modern large language models. So basically you have this x the previous input and xi xi plus 1, right? This is just the attention block of or the transformer block. You have a normalization layer. There is a mathematical computation happening here, and you have multi-head attention from the input, and then from this you sum the input and the multi-head attention, and you normalize this one, and normalize ታደርገዋለህ, and then you feed forward network, and you sum it with this the input and the ከኢንፑት ቀጥታ ከመጣውና ከመልቲሄድ አቴንሽኑ ጋር ከተደመረው ጋር ትደምረዋለህ፣ and ከፊድ ፎርዋርድ ከመጣው ሪዛልት ጋር ትደምረዋለህ, and then you get the output for your hidden layer. ይሄ ምን ማለት ነው? this output will be very ኮንቴክስቱን የተረዳ ይሆናል ማለት ነው። ይሄንን ስታክ ስናደርገው this multiple transformer ይሄንን transformer architecture ብቻውን it can only solve problems, but stack ሲደረግ together it will become the transformer architecture. Transformers or this is transformer block ነው ይሄ, so this will become transformer architecture. So እዚህ ጋር የምታዩት stacked transformer block ነው. This is also from the attention all you need paper. And input tokens, and you have an embedding or input encoding. You have embedding x1 and x2. then እዚህ ጋር እንደምታዩት እነዚህ ሁለት ግሬ እንትኖች layer normalizers ናቸው. This is the multi-head attention, and you have the feed forward output. you see እያንዳንዱ እርስ በእርሱ connected ነው. so it will learn the positional encoding, the ideas, the context, and the embeddings for everything, and afterward you will be able to predict the next word. so the መጨረሻው የlanguage model head, you will softmax over the possibilities of the next word, and you get you pick the highest probable word, or the model will pick highest probable word. So sometimes could be auto regressive ሊሆን ይችላል። ያ ማለት እዚህ ጋር the output of your one stack or your one stack could be used as an input for your next stack, and then the output from your next will go to as an input. This is auto regressive approach ይባላል። so basically a transformer, this is how transformer works, and this is how our language being generated. so አሁን ከትራንስፎርመርስ ደግሞ ከሊኒያር ሪግሬሽን እስከ ትራንስፎርመር ድረስ it took like hundreds of years evolve ለማድረግ። ግን once transformer happen ካደረገ ከ2017 በኋላ it was drastic, and it was a boom from there. so basically LLMs or large language models are built by scaling transformer models, right? so እነዚህ transformer architecture or transformer model ላይ more layer በመጨመር embedding layer በመጨመር training on a huge amount of data ላይ train በማድረግ ነው እነዚህ language ሞዴሎች create የተደረጉት ማለት ነው። So large language models are trained with next token prediction. Basically, it is the task of predicting the next token. And sometimes masked language model. So masked language model example, this BERT or bidirectional encoder representation transformer ይባላል. This is transformer based. Yeah, so the masked language model. So we will do a video on separately. This is በራሳቸው already ትልልቅ ቻፕተሮች ስለሆኑ እዚሁ ጋር እናልፋቸዋለን. But we can talk about it after pre-training. Models can be fine-tuned. አንድ ጊዜ ሞዴል ትሬን ከተደረገ በኋላ can be fine-tuned for a specific task. That means some weights will be altered and aligned via reinforcement learning. Yeah, so sometimes also RAG or retrieval augmented generations that yeah, contextual data ተጠቅመን LLMን communicate ስናደርግ ማለት ነው. I will also do a video and practical stuff on retrieval augmented generation. It's pretty nice. So customizing large language model for specific tasks could be prompt engineering ሊሆን ይችላል. Guide the model behavior using example and instruction. We can tell how they should act or how they should respond. In context learn or few shots. Show pattern in the prompt, so there's no weight update. Instruction tuning, so low ranking adaptation. Using adapters we can do that. That means already pre-trained የሆነውን architecture ወስደን some weights freeze አድርገን some layers freeze አድርገን only the yeah few extra layers በመጨመር or few extra ሌየሩን በመቀየር ቼንጅ በማድረግ አዳፕት ማድረግ ይቻላል ማለት ነው. yes yeah why local adaptation? ምክንያቱም large language model እንደምታዩት it's a lot of information and it's nearly accurate on everything. so ሁሉንም ነገር በወፍ በረር ሊያውቅ ይችላል. so ግን in specific domain ሲመጣ you have to adapt that, and the idea of doing that what I like is RAG or retrieval augmented generation. ይሄ ሌስ ሃሉሲኔት እንዲያደርግ የተሻለ ሪዛልት እናገኛለን. so how RAG work? ለምሳሌ you have a gigantic data set, ለምሳሌ ChatGPT or llama model is pre-trained, and you have the parameters and the weights there, the learned weights. so you have a base model, and መጀመሪያ we want a problem to solve, right? ለምሳሌ some sort of medical context ላይ ከሆነ RAG or retrieval augmented generator የምንፈልገው we want some kind of architecture that when we ask a question, this question will be answered from a specific document. ለምሳሌ I don't know ስለ clinical guideline በክሊኒካል ጋይድላይን ትሬንድ አይደለም ብለን ብናስብ the large language model will compile the compilation of clinical guidelines chunked into some chunks and put into a vector database, and from there መጀመሪያ የምናደርገው ምንድን ነው? we have a retriever እዚህ ጋር retrieval augmented generation, so we also have retriever model here. so ስንጠይቀው the retriever we go and retrieve from the document we provide based on how we calculated the relevance. የጠየቅነው ይሄን ጋይድላይን ስንለው እነዚህ ብሎ መልስ ጀነሬት ያደርግልናል the retriever. so we will get accurate retriever, and ይሄንን ሪትራይቭ ያደረገውን መልስ ለኤልኤልኤም or ለትሬንድ ለሆነው ለቢግ ሞዴሉ ይሰጠዋል። ያ ቢግ ሞዴል ከዚህኛው መረጃውን ይወስድና በምንፈልገው መንገድ ሪስፖንድ ያደርግልናል ማለት ነው። ሶ ለዚህ ላርጅ ላንጉዌጅ ሞዴል ቤዝ የሚሆን መረጃ የሚሰጠው what we store ነው። so the idea of RAG is in short it looks like this ይህን ይመስላል ያ